Now in this question we are given with these two figures, figure 1, figure 2. Now in this figure we can see that this normal force will going to change when this theta is changed. Now our aim is to determine the magnitude of this force F for each of these three curves shown in figure 2. When theta is changed, the normal force is changed. So by using both these two diagrams, we have to find the magnitude of this force F for these three cases A, B and C. Okay. So first I'll be applying the Newton's second law of motion in the vertical direction, and this direction I'm taking positive y. So I can write that sigma Fy is equals to 0. This is the net force in the y direction equals to 0 because there is no acceleration in the vertical direction. That is why the net forces in the vertical direction are 0. So in the y direction we have the normal force N, then the minus mg force, this is the weight force mg, and the component of this force Fy in the vertical direction is plus F sine theta, and this is equals to 0. Now from here we can simplify it for F, and the value of F will be equals to mg minus n over sine theta. Now if you see this curve A, this one, now when theta is 90 degrees, the value of n is half of mg. Here we see when theta becomes 90 degrees for this curve, the value of n is half of mg. So n we have 1 over 2 mg. So I'm solving the case A now. When n is equals to 1 over 2 mg, we can put the values here in this equation. So F is equals to mg minus 1 over 2 mg over sine theta, and theta we have 90 degrees. So that comes out to be as 1 over 2 mg. So this is the magnitude of force when n becomes half of mg and theta becomes 90 degrees. Now next we can solve the B part, and I'm writing here this is the B part. Now here we see that when this is the curve B. Now when theta becomes 90 degrees, the value of n normal force is 0 in this case. So we can put it here, n to be 0 here. So force F, this will be equals to mg over sine theta, and theta is 90 degrees. So this is equals to mg. So for the B part, the force F will be mg. Now for the third case, this is the third case. Now when theta becomes 30 degrees, n is 0. We can put it here. This is the C part here. When theta is 30, n is 0. So F will be equals to mg minus 0 over sine 30, and that is equals to 2 times mg. So this is the force for the third case. Now in this question we are given that there is a book whose mass is 2.9 kg and it is resting on a surface which is inclined at 36 degrees above horizontal. Now there are two parts in this question that we need to solve. In the A part, we need to find the normal force exerted on the book. So I'll be drawing the free body diagram for the book. So the weight force would be acting in the vertically downward direction mg, and this direction I'm taking positive x, this is positive y. The normal force will be perpendicular to the surface n, like this. Now if this angle is theta, so this angle will also be theta. I've discussed this concept in my previous videos multiple times, you can see over there. And now the component of this mg force along the y direction will be mg cosine theta, and the component of this mg force along the x axis will be mg sine theta. Now we have to find the normal force. Now in the y direction there is no motion or there is no acceleration, so sigma Fy is 0. So we can write that n minus mg cosine theta, this should be equals to 0, and from here n will be equals to mg cosine theta. Now m we are given to be 2.9 kg, g is 9.81 times cosine theta is 36 degrees, and from here this normal force comes equals to 23 Newton. Now next, in the B part, they are asking if the angle of inclination is reduced, then the normal force will increase, decrease, or stays the same. So if this theta is reduced, then this cosine theta will going to increase, and if cosine theta increases, the normal force will going to increase. Thus for the B part, normal force increases. Now in this question, we are given that this is an ant that walks slowly away from the top of the bowling ball, as you can see here. Now if the ant starts to slip when the normal force on the feet drops below half of its weight, then at what angle does slipping begins? To solve this problem, we're going to use the Newton's second law of motion, and we're going to apply the Newton's second law along the radial direction of the circle. So if you consider the free body diagram, this is the ant. Normal force will be perpendicular to the surface, this is N, and its weight force would be acting in the downward direction, mg. Now if this angle is theta, so this angle will also be theta, and the component of this mg force along the radial direction will be mg cosine theta. Now from the Newton's second law of motion, we can write that the net force along the radial direction, this is mass times the acceleration, and since acceleration is 0, so this term is 0, or we can write that sigma fr is equals to 0. Now along the radial direction we have two forces, N and mg cosine theta, and this direction I am taking positive, so we can write that N minus mg cosine theta is equals to 0, and in the question it is given that N becomes 1 over 2 mg, half of the weight force. So 1 over 2 mg minus mg cosine theta is equals to 0. Now from here 1 over 2 mg is equals to mg cosine theta. This mg and mg will cancel, and we'll get that cosine theta is equals to 1 over 2, and from here theta would be equals to 60 degrees. So this is the required angle theta where the slipping will begin. Now in this question it is given that you are riding in an elevator which is moving upwards with an acceleration a. Now you begin a game of darts that you can see here. Now we have to tell that do you have to aim your darts higher than, lower than, or same as when you play darts on the solid ground. So on the solid ground the acceleration is 0, right? But when you are in the elevator is accelerating upwards with an acceleration a. So the correct answer would be that you have to aim your darts higher than as compared on the solid ground, and the reason is this one. The first option is correct, that for the case for this case the elevator is moving in the upward direction and the apparent weight of the dart is greater than its actual weight mg, and therefore you have to aim your darts higher than you play darts on the solid ground. This is the correct option. Other two options, if we see, second option, it says that you have to aim lower to compensate for the upward acceleration of the elevator. This is totally wrong. Next it says that since the elevator moves with constant acceleration, Newton's laws apply within the elevator the same as on the no. So this statement is also wrong. Only this one is correct.